everyone, welcome to today's videos. We're going to talk about quantum chemistry. But when people talk about quantum, they often refer to famous scientists like Einstein or the confusing theory. And of course, how hard this field is. It is true though, but when we dive deep and do further research, we also find the interesting area like quantum chemistry. And of course, quantum physics is often refers more than quantum chemistry. So in these videos, we aim to give an overview of quantum chemistry. A wave is a disturbance that travels through a space of matter, transferring energy without transferring matter. The highest part of the wave is called a peak, and the lowest part of the wave is called trough. An amplitude, or the maximum displacement from the neutral position, or we call it the height of the wave. Wavelength is a distance between two consecutive peaks and or identical part of the wave. The highlight part of the diagram, we call it an oscillation or a cycle. A frequency is calculated by the number of repetition or cycles per second in hertz. A velocity of the wave is a product of wavelength time frequency. Since there are different wavelengths in electromagnetic, it's been represented by electromagnetic spectrum to give you a clearer picture. The electromagnetic spectrum covers since the low frequency or very long wave, like radio wave, until the very short or high frequency wave, like gamma ray. But human eyes can only detect the small portion of this spectrum, and we call it visible light. Light energy. Light is defined as electromagnetic radiation with a wavelength between 380 and 750 nanometer, visible to human eyes. Light contains photons, which are minute packets of energy. When an object's atom get heat up, it produces photon. The electron find excitement from the heat, which result in earning extra energy. The energy is released in the form of photon, and more photons come out as the substance gets hotter. Quantum theory of light was proposed by Einstein. It stated that light travels in a bundle of energy, and each bundle is known as photon. Each photon carries a quantity of energy equal to the product of frequency of vibration of that photon and Planck constant. Maxwell theory. The theory describes the interaction between electric field and magnetic field. James Maxwell proposed that light waves have electrical and magnetic property, can travel through the vacuum, or in another word, do not require a medium for transmission.
Planck's theory. Planck's quantum theory is a fundamental theory in physics proposed by the German physicist Max Planck in the year 1900. The theory explains deep through the nature of light and energy and laid the foundation for the development of quantum mechanics. Planck's theory proposed that different atoms and molecules can emit or absorb energy in discrete quantities only. The smallest amount of energy that can be emitted or absorbed in the form of electromagnetic radiation is known as quantum. According to this theory, the energy of a single quantum is proportional to the frequency of the electromagnetic radiation it represents, where the constant of proportionality is now known as Planck's constant. Famous German physicist Albert Einstein revised Planck's theory in the year 1905 in order to better explain the photoelectric effect. He believed that if a light source were directed at specific materials, the light would cause the material to emit electrons. In essence, Planck's research helped Einstein realize that discrete energy units called photons, or units of light, exist. Planck also created a formula that is used to calculate the energy of the radiation, which is E equal to hv, where E stands for the energy of the radiation, h stands for Planck's constant, and v stands for frequency of radiation. Planck's quantum theory has numerous applications in various fields, including physics, electronics, computing, and material science. Planck quantum theory explains the behavior of subatomic particles and provides insights into the properties of particles such as photons, electrons, and atoms, which are crucial for many areas of science, including quantum mechanics and nuclear physics. The second one, it's important to the development of lasers. Lasers are widely used in industry, medicine, and research. Lasers work by emitting light in a highly concentrated and coherent form, and their design and operation rely on quantum mechanics. The third one, it leads to the development of quantum computing. Planck's theory is the foundation of quantum mechanics, which is the basis of quantum computing. Quantum computers are expected to provide significant advantages over classical computers in solving complex problems. And the development of this technology relies heavily on Planck's quantum theory. Planck's theory was initially developed to explain the observed spectrums of blackbody radiation. What is blackbody radiation? A blackbody radiation is a body or object which absorbs all the radiation falling on it. All frequencies of radiation are absorbed and emitted by a perfect black substance. Temperature affects how much electromagnetic radiations a blackbody emits. Planck's law can be used to explain the frequency variation of the radiation that a blackbody emits. Planck's radiation, a form of thermal radiation, is another name for this kind of radiation. As temperature varies, the body emits more radiation of all wavelengths at higher body temperatures. A blackbody radiation has a wide range of applications in many fields, including physics, astronomy, engineering, and material science. The first one, in an astronomy field. Astronomers use blackbody radiation to study the temperature and the composition of stars, galaxies, and the other objects in the universe. Secondly, thermal radiation matters. Blackbody radiation is used to model thermal radiation emitted by objects at high temperatures. This is used in many industrial and engineering applications, such as in the designs of furnaces, incandescent light bulbs, and space heaters. Lastly, climate modeling. By modeling the blackbody radiation emitted by the Earth and the Sun, scientists can better understand the factors that contribute to climate change.
Now, we are going to talk about photoelectric effects. In 1905, Albert Einstein stated that light can be seen as quanta of energy that behave the particle. An electromagnetic radiation, photon, is particle with zero mass and carries a quantum of energy. According to the E equals to h multiplied with v equation, light photon energy is quantized. It was challenging for scientists within classical physics to fully accept the idea that light could also be represented as both waves and particles. The photoelectric effects is a crucial idea that Einstein clarified using light particle nature. When light shines on metal surface, electrons can be ejected from the surface of metal in a phenomenon known as the photoelectric effect. In terms of their behavior and their properties, photoelectrons are not different from other electrons. So the prefix photo tells us that electrons have been ejected from a metal surface by an incident light. Consider the Planck equation, which states that E equals to h multiplied with V equation. The E indicates the lowest energy need for the metal surface to be ejected. If the frequency of the incoming light V is less than threshold frequency, there will be not enough energy to cause electrons to be ejected. Electrons will be ejected if the frequency is equal or greater than the threshold frequency. So the ejected electron only travel faster when the frequency lies over the threshold frequency. An increase in the intensity of incoming light over the threshold frequency generates an increase in number of electrons expelled, but they don't move any quicker. The photoelectric effect is used in photoelectric cells, which are widespread in our everyday products, such as calculators that use light energy to create electricity. Niels Bohr proposed the Bohr model of the atom in 1915. It was created by modifying Rutherford's atomic model. Theory established the nuclear model of an atom, in which a positively charged nucleus is surrounded by negatively charged electrons. The atomic structure model was modified by Bohr theory, which indicates that electrons travel in fixed orbitals, and each orbital has fixed energy. Rutherford described an atom nucleus, and Bohr expanded on the concept to include electrons and their energy level. So now, let's talk about future of Niels Bohr atomic model. Electrons, which are negatively charged particles in an atom, orbit around the positively charged nucleus in a specified circular path called orbital or shell. The energy levels are expressed by an integer n equal to 1, 2, 3, known as the quantum number. This quantum number range begins on the nuclear side with n equal to 1, having the lowest energy level. The orbit n equal to 1, 2, 3, 4, known as K, L, M, and shells. And an electron is said to be in ground state when it occupies the lowest energy level. Electrons in an atom gain energy when moving from a lower energy level to a higher energy level. And electrons lose energy when they move from a higher energy level to a lower energy level.
Now, moving on to electron shells, as Daniel said earlier about the history of electron shells, then I am going to be explaining what are electron shells. So, an electron shell simply is the outer portion of an atom that surrounds the atomic nucleus, and the orbital routes that electrons take around the nucleus are known as the shells. So, electrons like to take the path of least resistance, just like everything else in chemistry, and this indicates that electrons often fill an atom's shell from the inside out, working its way from the lowest to the highest energy level. And there is always a maximum number of electrons that each shell can take in. So like, for example, the first shell can take in 2 electrons as its maximum number, and the second shell can take in 8 as its maximum number, and the third shell, etc. So when discussing about electron shells, we refer to the outermost one as the valence shell, and the behavior of an element in forming bonds depends on the electrons present in this shell. So a valence shell that is completely filled is typically a sign stating that the atoms is stable. And interestingly, the number 8 holds significance when it comes to this shell. So most elements follows the octet rule, right, which states that an element should have 8 electrons in its outermost energy level to be able to be stable. Lastly, energy levels are split into subshells, and each energy level contains a certain number of subshells. Subshells are smaller parts within each electron shell, and the most common and the first 4 subshells are S, P, D, and F. Since we know that each electron shell has its own energy level, when the principal quantum number increases, the shell increases in energy level as well. This is the same for each subshell within a shell. So subshell has the highest energy level among the subshell D, P, and S. Moreover, each subshell will have an energy level that is lower than the shell above it.
Next, we are going to be talking about degenerate orbitals. Degenerate orbitals are used in quantum mechanics with the meaning of equal energy, which usually refers to the energy of electrons. Degenerate orbitals are electron orbitals that have the same energy level. There are 3 principles that apply to this theory. The first one is Aufbau principle. It states that we should fill up the electrons in the lowest energy orbital before filling up in the higher energy orbital. The second one is Hund's rule. It states that every sub-energy is singly occupied before it is occupied doubly. The last one is Pauli's exclusion principle, which states that to occupy the same orbital, 2 electrons must have the opposite spin, and electrons must be paired. You can see in the picture that arrows are pointing in different directions. It indicates the direction of electron orbitals. Degenerate orbitals can indicate the elements, group, and period. If the electrons fill up to 2s or 2p, then it means that it is on second period. And to indicate the group of the element, you must add the electrons from the highest degenerate orbitals, such as 2s and 2p, and you will get the groups of electrons. For example, nitrogen. You can see that its orbital fills up to the first sublevel and reaches 2p. This means that it is in period 2. You can also find the group of the element by adding the degenerate orbitals from 2s and 2p together. We can see that the element is in group 5. This shows us that nitrogen is in period 2, group 5.
Next, let's move on to an extra theory of the quantum chemistry. As chemistry is the consequence of the behavior of electron bonds in atomic nuclei, chemistry becomes a simple matter of applied quantum mechanics, since it has been known and recorded that those behaviors of electron bonds to atomic nuclei can be determined according to the rules of the quantum mechanics. One of the topics related to quantum chemistry is the vibrational frequency and intensities, the molecular structure, the type of chemical bond, the intramolecular forces acting between atoms in a molecule, and the intramolecular force in the condensed phase can all be learned using vibrational methods. The study of molecular vibrations using classical and quantum approaches has attracted a lot of interest from theoretical chemists. This technique has been applied to a variety of tasks, including the calculation of precise force field, the prediction of the frequency and magnitude of rotational and vibrational bands of molecules in harmonic and anharmonic approximations, the assessment of vibrationally averages property and thermodynamic functions, and also the calculation of many body potentials. In addition, the vibration can be applied to string theory, seeing that the string theory attempts to merge quantum theory and quantum mechanics with Albert Einstein's theory of relativity. Besides the quantum universe that is used to explain nature at the most fundamental level, providing the description of the universe in microscopic or subatomic scale. Superstrings of the string theory can be used to predict undiscovered dimensions of space, shaping the concept of gravity. Searching for an extra dimension and exploring their properties can test the validity of string theory, as the string itself is too tiny to observe directly.